Hi, let's go to chapter 9.2, centripetal force. Okay, what we have learned in chapter 9.1, we have learned centripetal acceleration. And we have the equation, this is given in the public exam. Centripetal acceleration, A equal to V squared over R equal to R omega square. Okay, and we have Newton's second law, net force equal to ma. So the required force for the object to move in a circle is mv squared over r, or mr omega square. This force is called centripetal force, 向心力. Okay, maybe you can try an experiment by yourself to feel the centripetal acceleration. Okay, you can wound an object on a string. Okay, then your fingers will have to pull the string inwards. Okay, then you feel you have exert the centripetal force on the object. Okay, without this centripetal force, what do you think about the object? You see, you will move in a straight line, go away. Okay. Now, for the centripetal force, actually it's not a new kind of force. It comes from something. For example, if you wound the object in a circle like this, the centripetal force comes from tension. Okay, and the centripetal force always point towards the center. Okay, which is perpendicular to its movement of the object. Okay, as what we have learned in chapter 9.1, we have said that the centripetal acceleration points toward the center. Okay, and F equal to ma, so the centripetal force is also point towards the center of the circle. Now, let's look at example 3. Okay, now you see there is a microwave oven. The object, the plate here, is moving in a circle. Okay, so the bed is 0.2 kg, and it changed 80 degrees in 4 seconds without slipping. Okay, and R is 10 cm. Okay, find the angular speed. Angular speed omega. Okay, now you need to remember the equation, right? Omega. So how can we find omega? So omega equal to theta over t. So we have to find out the omega in terms of radian. Okay, so 80 degree here, so times 2 pi over 360 degree. Okay, in 4 seconds. So we get the answer 1.396 radian over 4 seconds. So it will be 0.349 radian per second. So this is angular speed. Okay, find the centripetal force. Okay, now actually, now if I draw side wheel, okay, the black is here, the center here. Now it undergoes circular motion, right? Okay, which force give the centripetal force? Any tension here? Okay, no. So which force? Now if you draw the three-point diagram of the bed, how many force added on it? So normal force, weight, and also friction. Okay, so friction will be in this direction. Without friction, the bed will slide away, okay, from the turntable. So the friction make the bed to move in a circle. So now we have friction here. Friction. Okay, friction gives the centripetal force. So centripetal force here is equal to friction. Friction equal to, now we have calculated omega. So we can use the equation mr omega square. Okay, so now m 0.2, r use SI unit, 10 cm means 0.1 meter, omega 0.349. Okay, here square, don't forget square. Okay, mr omega square. Then we get the answer 2.44 times 10 to the power minus 3 Newton. Okay, and the last part, and where does the centripetal force come from? Okay, so you see from the picture, it comes from friction. Okay, now let's try chapter 3. Okay, try question 1 only. You may pause the video and have a try. Write the answer on your textbook. Okay, now so now we go to the answer. So you see a ball is connected to a fixed point O, and then it perform a circular motion. Okay, smooth turn horizontal table. That means no friction here. Okay, so where does centripetal force come from? It comes from tension. Okay, tension. So now we have a string 0.15 meter, and we have mass 0.2 kg, and we have tension 5 Newton. So what is linear speed? Okay, so we have a centripetal force equal to mv squared over r. This centripetal force comes from tension. So tension equal to mv squared over r. So by substitution, 5 equal to 0.2. V is unknown. Okay, R is 0.15. So we get V equal to 1.94 ms mass 1. Okay? Verify equation of a centripetal force. Okay, so maybe we go to the experiment first. Then we go back to the equations. And now this is SPA experiment. Okay, you need to weld the rubber band. Okay, here. Okay, move in a circular motion. Okay, like this. The rubber band move in this direction. Okay, and you can see the tension actually give centripetal force, and the tension is at some angle, right? So the Tx, we have to resolve Tx and Ty component. Tx gives centripetal force. Okay, and the tension is provided by the can be calculated by the weight of these screw nuts. Okay, now maybe we look at the video first.
We will make a centripetal force apparatus using the materials shown. Measure the mass of the screw nuts and the rubber bung with an electronic balance. Connect the screw nuts and the rubber bung with a piece of nylon string. Set the distance L between the rubber bung and the glass tube to 1 meter. Mark the length with a paper marker. Whirl the rubber bung horizontally. Remember to keep the paper marker just below the glass tube. Record the total time needed for 50 revolutions and calculate the angular velocity of the rubber bung and the tension in the string. Repeat the experiment with different lengths. Does the equation for the centripetal force hold for different values of L?
Okay. Actually, this is SB experiment. Okay, how can we verify the equation of centripetal force? Now, you see, in this case, we have tension. Okay, and also we have weight. So two forces acting on the rubber band, tension, weight. Okay, and you can see the object is moving in a horizontal circle. So we can, we can resolve T into two components. That is Ty and Tx. Okay, Ty and Tx, Ty, Tx. Okay, vertically, no net force. Do you agree? Otherwise, it will go down or go up. Okay, no net force. So we have the equation here. Ty equal to weight. Okay, because we have to resolve T into Tx and Ty. And Tx actually would give the centripetal force. So mv squared over r log, or mr omega squared. Okay. Now here we have learned how to resolve the component at the beginning of Form 4, right? So Ty would be T cosine theta. We have theta here. Okay, so theta here. So T cosine theta will be equal to mg. Okay, and T sine theta will be mr omega squared. What can you see about sine theta? Now look at this angle. Look at this triangle. Okay. So we have sine theta equal to, here, sine theta equal to r log over a log. Okay. So for the equation, we can have T r log over a log equal to m r log omega squared. So T equal to m a log omega squared. Okay. But here, this T is tension. We can find out tension in the experiment. Okay, as you know, here, when you look at this part, tension is equal to, suppose the screw nuts has a mass of M, capital M, equal to mg. Okay, T equal to mg. So we have the equation here. T equal to ml omega squared, while this T is equal to mg. Okay, equal to mg. So we can find out by using an electronic balance. So you can find out. Okay, small m is the mass of rubber band. We can also find out L we can measure the length of strength, so we can find out omega. We can use 2 pi over t. Okay, we use a stopwatch to measure the angular speed. So we can also find it out. So if the left hand side of the equation here, t, equal to ml omega squared, then we can verify the equation of centripetal force. Okay, now this is your SBA task. Actually, you can prove it by yourself, and you have to write down your proof in the SBA. Okay, now for this chapter with these two equations, t cosine theta and t sine theta, this is quite important. Now, let's look at some funny experiment. Centripetal force and Newton's first law.
There are a thin layer of small beads and a particle circular rail in a tray. Place a ball against the rail. Strike the ball to make it move along a circular path. What will happen when the ball leaves the rail? Watch the motion again from the other angle. When the ball leaves the rail, the normal reaction acting on the ball by the rail disappears. As a result, the ball moves in a straight line due to inertia.
Here you see the object is undergo a circular motion. Okay, so which force give the centripetal force? It will be the normal reaction by the metal wheel. Okay, here give the centripetal force. Okay, so the object can move in a circle, but at the end of the wheel here, okay, we find that there is no normal force here, okay, because it's leaving away from the wheel. So without the normal force, what happened? So there will be no centripetal force. So by Newton's first law, no net force acting on it, no centripetal force here, no net force. So the object would travel in a straight line. Okay, it's inertia, right? So it moves in a straight line. Okay, the normal reaction disappear. The ball continue to move in a straight path. OK， 好啦，正如如果頭先呢一個揈下個波，如果我突然間放手點啊？咁個波會直飛過去啊。OK， 嗱maybe you try checkpoint 4. OK, pause the video, try checkpoint 4. OK, we may try the answers later. Okay, now let's check the answers. So in this case, figure A, what is the tension in the string? So here, maybe you can let the angle theta, and this is R. Okay. So you can have two equations about that. It can be so we have to draw the three-point diagram with tension and weight, okay, for the object. Do you agree? Tension, weight, okay. So theta here. So tension theta would give the centripetal force mr omega squared. tension cosine theta equal to mg. Okay, balance the weight. Otherwise, the object would move down. Okay, so you have two equations before you go further. So what is the tension? Okay, now here now we have 50 over 1000 kg. Okay, R 0.3 meter. So 5 revolution 2 seconds. So what can you find? You can find omega. Omega equal theta over t. Okay, 5 revolution. So 5 times 2 pi. 5個圈啊。Okay, over 2. So it would be 5 pi. So by substitution, t. Okay, now we have sine theta here is equal to r over 0.3. Can you see that? Here, okay. So by substitution, t r over 0.3 equal to m r omega square. Okay, so here we can delete r, right, in both sides. So you can use your calculator to find the answer. Okay, it will be 3.7 Newton. Okay, and for question 2, C, okay, C, go straight line. Because of inertia, no net force, so you move in a straight line. Okay, so this is the first half of chapter 9.2. And for the next half will be the example of this circular motion.